possible. Welcome to Unit 3, Lesson 6. As usual, please look for the tasks to complete for U3L6 on Canvas, either on the home page under today's date, which is the 30th of November, or under assignments. We're going to start off like we usually do with a quick breakout room chat. The question for today I just put up in the chat. It is, if you could pick up a new skill in an instant, what would it be? Have you guys answered this yet? Is this one you've done? No? Okay. So again, if you could pick up a new skill in an instant, think like the Matrix, like, whoa, I know Kung Fu, like download it into your brain. What would it be? Again, it could be cooking, could be a language, could be whatever you consider a skill. I have a broad definition of what a skill would be. So, Bryce, how are things?
Things are good.
What's one thing you did over the 5-day weekend?
I had a lot of things, but I guess I went to the beach a few times. So
Nice. Weather was pretty good over here. All right, everybody. Breakout rooms are open. We'll come back together in about 2 minutes. All right, next we are actually going to start off once again with a formative assessment probe, just like we did in our lesson before we went on the long weekend. So we're on tasks to complete step number 2, the formative assessment probe. Again, remember these are graded for completion, not for correctness. So don't worry about that. I just want to get your thoughts as you currently stand. So you don't need to look up anything. You don't need to look at your notes. Just write down your understanding. The title is Why Does It Rain? I'm going to give us 10 minutes to complete this, so hopefully it won't take that long. We'll come back together to check in. So 10 minutes to complete the Why Does It Rain, or Why Does Rain Fall formative assessment probe. Go for it. Let me know if you need help. Drops. They become too heavy and they fall down, which is what Marcus is getting at. So again, we'll kind of keep reinforcing this with the readings, but glad to see most of you are feeling good about that. Any questions or comments on that formative assessment probe? Next on the docket was homework. You had to make sure you've submitted your Cloud in a Jar video. I'm seeing 10 responses. So a few of you, maybe you emailed me your videos, but get that done if you have not done so yet. The Ed puzzle as well needs a little more attention. I'd say about half of you actually have it completed. So that's something that you're going to need to either use class time today to finish up or continue working on for homework. But please get that done. It's just nice review of chapter 26.8, the most recent chapter we covered, which we're going to continue to explore today. Any questions or comments on those homework assignments? All right. We are now going to sort of change gears. We've been talking about water in the atmosphere, and so it's high time that we got into a little bit more chemistry and started to talk about states of matter and phase changes. I'm going to use my iPad to quickly review some slides and use some poll questions as we've done before. And then I'm going to let you go for a little online simulation activity. Let's see here. Again, just going to need verbal confirmation. Everyone's seeing slides moving rapidly in front of them?
Yeah.
All righty. So let my computer catch up. All right, take a look at this graph. Is anyone brave enough to tell me, what is this graph? What's the joke this graph is making? I'm going to call on a victim if no one else volunteers here. Noah, what are your thoughts?
That the temperature starts at 100 degrees Celsius and drops after 4 minutes.
So if there's any tea drinkers out there, right? When you make tea, it's usually way too hot, and so you wait a few minutes, and then what happens? Suddenly it's way too cold. And there's never like a moment where it's that perfect temperature. Anyway, kind of stupid, but just showing you a joke through a graph comparing temperature and time. So if you're going to understand temperature, though, we have to talk about what's called kinetic energy, which I'm hoping most of you understand is the energy of motion. Anything that is moving has kinetic energy. This is different from potential energy, which is the energy of position, right? This bicyclist, when they were sitting still on their bike at the top of the hill, had potential energy, but once they started to ride down the hill in motion, moving, they have what's called kinetic energy. And kinetic energy also applies on the molecular level, right? You can think of liquids and gases as little tiny elements and molecules that are always moving. That gives them kinetic energy. Temperature is just the measure of the average kinetic energy that particles have. So that's kind of a key definition to keep in mind. When we're measuring temperature, we're just asking ourselves how active are all the little atoms that make up that substance. So when things are hot, that means all the particles or atoms in the matter are moving really quickly. They have lots of kinetic energy. When something's cold, it means they're not moving very quickly and have lower kinetic energy. Now, what's a little weird to think about though is when you have a reaction or something that is absorbing heat, we call this endothermic reactions and that kind of thing. When you touch them, they're going to feel cold. And that's because your finger, right, is having warmth removed from it, right? If it's absorbing heat, when you touch this thing, this reaction or an object, it's going to remove heat from your hand. So it's going to feel cold to you, even though it's technically gaining energy, right? It's taking energy from you. And that's why it feels cold to us. Vice versa, right? Releasing heat or a reaction that releases heat or transfers heat, when we touch that, right, if you touch a beaker or something, it's going to feel warm. We refer to this as exothermic. Exothermic. But even though it's losing energy, it feels warm to us because it's releasing that energy into your finger when you touch the beaker or whatever, wherever an exothermic process is occurring. All right, I'm hoping you're familiar with the states of matter: solid, liquid, gas. It's pretty straightforward. There is a fourth one called plasma, but we're not going to touch on that yet. Solids, as you would expect, have very low kinetic energy. Their molecules are not moving very much. Technically, they're vibrating in place. That's why they have that little kind of shaking animation there. They can take any shape, so you can have a rock in a glass and pour it out onto the table. It will not change its shape. It always has that. Very strong attractive forces between the molecules, and they're so packed together, they're so close to each other already that they cannot be compressed. Now, what that means is you cannot shrink the volume. So if I was able to take the perfect volume of, again, let's say a rock that I've got, you could not crush that into a smaller volume. You could crush it into a fine powder, but if you tried to, again, squish that powder into a smaller volume overall, it's not going to happen. You can't compress solids. Liquids are very similar to solids. I want you to kind of get that mindset. They have a little bit of kinetic energy, more than solids, but on the grand scale, not that much. The molecules are just sliding past each other, as you can see in this little picture here. They still have very strong attractive forces between them, which is why you get these little droplets and things like that, especially with water, which is polar as well. They will take the shape of their container. So liquids are pulled down by gravity. So if you have a glass and pour it on the table, it'll flatten out in response to gravity. And likewise, they cannot be compressed. Technically, liquids are a little bit compressible, but again, I want you to associate them with solids. Think of the particles as so close together that you can't use pressure to significantly reduce the volume, right? You can't shrink a liquid down. Gases are completely different. We're going to spend a very long time talking about gases because they're pretty cool. They have incredibly high kinetic energy. They move very rapidly and randomly, the particles, as you can see in this picture here. There's lots of space between them. They will take the shape of whatever container they're in, or if they're not in a container, then they'll just float around in the air, in our atmosphere. They have little to no attractive forces between them, and they can be compressed. So if you're able to capture a gas into a smaller container, you could potentially shrink its volume or increase its volume. And that's because there's so much space in between them that you can crush these molecules down and make them a little closer to each other, though that is going to increase what we call pressure, which we're going to talk about a little bit later. Okay, first poll question should now be available on the screen. Give that a go. All right, 14 responses. Here are the results. Looks like we're a little divided. Again, this is a very confusing thing. So in a reaction where heat is being lost or released, so whatever is happening, it's giving out heat. A transition from high to low energy, it would feel what? So again, this is something that is releasing heat. If you were to touch it, it would feel warm. So the correct answer was warm to the touch. I know everyone wants to think cold to the touch because it's losing energy. That's not the case. And in fact, something like a refrigerator, if you've ever touched the machinery on the back of a refrigerator, it's actually incredibly hot. That's because it's sucking and releasing all that heat from the food and stuff you've got in the refrigerator itself. Okay. Any questions so far? This is a little summary table of what I just talked about, referred to as kinetic theory. Again, it just compares the three states of matter. Again, there is a fourth one, plasma, and just everything that I was just talking about earlier. So this is a good thing to refer back to if you're confused by any of that. These are the classic images that you see representing solids, liquids, and gases, showing you how the particles behave. Again, you can hopefully notice in this that solids and liquids are actually very similar to each other, whereas gases are completely different. And so we're going to spend more time on gases talking about that. But just think of very high kinetic energy versus low or lower kinetic energy for solids and liquids. All right, got to know your phase changes. I'm hoping most of you are familiar with this already. So can anyone help me out? What do we call the transition from solid to liquid? What do you call that?
Melting.
Very good. The fancy term for it is called fusion. If you ever hear that word fusion, not in a nuclear context, then it is actually just another term for melting. All right, what's the next step? What do you call it when you go from liquid to gas? This is a trickier one.
Evaporating.
Evaporation is one form. You can have boiling as well. The catch-all term, right, that describes all of that, evaporation, boiling, is actually called vaporization. This is why these popular e-cigarettes that a lot of people are getting into now, which are just taking a liquid and converting it into a gas, they're called vaporizers, right? So vaporization is liquid to gas. All right, what's the opposite then? What do you call it when you go from gas to liquid? What happens on the side of a Coke can?
Condensation.
Very good, condensation. I'm not going to write it all out, but that's that. And then what do you call liquid to solid?
Freezing.
Very good. Or again, the more scientific term you will see is solidification. That's kind of a clear term for it. Now, anyone know what you call the jump if you went from solid straight to gas? This is what dry ice does. It's referred to as sublimation. The opposite of that, going from gas straight to solid, which, if you see frost forming and things like that, is called deposition. Like you're making a deposit in a bank. All right, so you need to be familiar with all of those terms. I'm hoping you pretty much are. They're pretty straightforward at this point. The important trend to understand is that going this way, so vaporization, melting, all of that requires an increase in kinetic energy. So we're adding more kinetic energy to it. The reverse, going backwards this way, solidification, condensation, freezing, requires a decrease in kinetic energy. And so we can categorize all these transitions with that. So anything that involves heating, right, an increase in kinetic energy, we're making the particles more active. That includes melting, vaporization, and sublimation. Again, that's just making the molecules move apart more, vibrate more, and spread out ultimately. The opposite of that then is cooling, where we are decreasing the kinetic energy, right? The particles are not moving as much. So solidification, condensation, and deposition are taking molecules that are very excited and moving a lot, slowing them down, forcing them closer together. And so this is kind of a nice little general summary where, again, you can see heating being removed or heat being added and causing those different transitions, and shows you what's happening on a molecular level. So it kind of brings together the two things we were just talking about. All right, next poll question now on the screen. Give that a go. Okay, seeing 13 responses. There we go, 100%. All right. Good. Looks like most of us are feeling good about this. Sublimation is the correct one. That's when you go directly from a solid to a gas. If you've ever seen dry ice, looks like it's kind of creating that smoke that you often see in Halloween and like the drinks people make. Or if you play with dry ice before, it kind of dances around on the table, and that's because it's going straight from solid, looks like a little white ice cube, straight into gaseous form. There's no liquid state, at least not at sea level pressures. All right. Any other questions or comments so far? All right, one more set of slides and one more poll question, and we'll wrap it up. Okay, so we can now bring pressure into the picture. You're going to get familiar with what are called phase diagrams. This is an example of a phase diagram. This is a phase diagram for water. But what phase diagrams are showing you is literally what they sound like. The phases are the states of matter. So it's showing you the temperature and pressure at which water will be either solid, liquid, or gas, right? So here's temperature on the bottom, and here's pressure on the side. And so not surprising, right, at sea level, that's what this is. At 0, right, that is technically the freezing point for water, right? So water will be ice at that point. And as you all know, if you can heat it up to 100 degrees Celsius, it will turn into vapor at that point. That's the boiling point. So this is just a measure of that. And so these lines are showing you those transition points, right? So these are the condensation or boiling point. This is the freezing or melting point. But what's cool is this one point right here where you have all three things happening at once. And this is what's referred to as the triple point. The triple point is technically the spot where you can get all three states existing at the same time, solid, liquid, and gas. And all transitions are happening rapidly at the same time. So it's boiling, condensing, melting, solidifying all at once. It looks kind of chaotic. I should be able to pull up this YouTube video here. Let's see if this works. But this is going to show you what's called cyclohexane. Oh, I guess it froze on me. All right, I guess I lost it completely. Well, you can check that out. I don't think I can actually click on the link there, can I? No. It's a cool video just showing you again the transitions. If I can get it uploaded again quickly, we can look at it, but I want to move on. Now, note, not every single phase diagram is the same. So this one was for water, I was showing you before. This is this phase diagram for carbon dioxide. And hoping you're noticing that, you know, again, look at the shape of the transitions for water versus look at the shape for carbon dioxide. Very, very different, right? As you know, carbon dioxide typically in gaseous form, right? That's how we interact with it in our atmosphere. And it requires very, very high pressures, right? If you're going to ever see a liquid form, which you can actually do in the laboratory. It's something we would have done if we were on campus. Okay, and once again, you can label all the transitions. I'm not going to take the time to do this, but you can kind of use that to test yourself. You're going to have to do something like that in the homework. But not surprisingly, if you're not sure how to fill something in, usually again, it's always temperature on the bottom and pressure on the side. And anytime you see low temperatures and high pressure, it's a safe bet you're going to be talking about solids. The middle area is always liquid, and anything that has low pressure and high temperature is going to be gas. And so then it's just those same transitions, right? Going from solid to liquid is melting, or liquid to solid is freezing. Liquid to gas, vaporization, gas to liquid condensation, and then sublimation, deposition down here. But again, there's your triple point where all three would be occurring at once. Now, specific heat is a whole other concept that we could spend a lot of time on, especially if this was a chemistry class, but I'm just going to give you the definition of it. Specific heat, represented by the letter C, is the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So in other words, this is basically how easily does something heat up. Think of it that way. And so, not surprisingly, interesting. This is all based on water. So water has a specific heat of 1 calorie per gram degree Celsius. There's also, it can be measured in joules as well, but again, don't worry about that. We're going to learn how to convert from calories to joules a little bit later. But what I'm hoping you notice is that liquid water has one of the highest specific heats. It's very, very hard to heat up water. It takes a lot of energy and a lot of time. Whereas, not surprisingly, certain metals like silver and mercury, if any of you have had silverware, anything like that, if you leave that out in the sun, even for a few minutes, it heats up really quickly, right? Iron, silver, they transfer heat quite easily. That's why we make cooking pots out of them and all that sort of stuff. So everything down here heats up really easily. Everything towards the top of the scale requires a lot more energy to change its temperature. And so that's really helpful on planet Earth, right? Because we've got the ocean. Water has a very high specific heat, which means water is very good at absorbing warmth while not changing its own temperature very much. And so this allows oceans to rapidly cool down the atmosphere and the air and absorb a lot of that solar radiation coming from the sun. And you can literally see this if you look at average temperatures in different parts of California, where most of you are. So take a look at like Santa Barbara average temperatures and San Francisco average temperatures. Now compare that to, even, well, Death Valley's like Barstow, Blythe, but yeah, even Death Valley. What's the difference? Well, obviously it's much cooler in San Francisco and Santa Barbara, much hotter in places like Death Valley, Barstow, and Blythe. What's making the difference? Proximity to what? Oops. Hopefully you're able to see my, I don't know why it stopped sharing there. So what makes a difference? Why would it be so much cooler in San Francisco or Santa Barbara compared to like Barstow or Blythe? What are San Francisco and Santa Barbara much closer to? Go ahead, Camille.
Ocean.
Yes, right? Ocean water makes a huge difference. Were the slides not visible for those last few minutes?
No, not for me.
Oh, okay, shoot, someone should have spoken up. Sorry. I think trying to play that YouTube video like messed it up. So, all right, well, again, just you can, there's a video I made of me going through these slides, which you're welcome to go back and refer to. I'll also put a link to the actual slides in the task to complete. I don't think I did. But you'll be reading about this and reviewing a lot of it for homework as well. I want to make sure that you have time for the activity that we also had planned. So one last poll question, just to see if you did pick up on any of this. Should now be on the screen. All right, I've seen 13 responses, good enough for me. All right, again, it looks like we're a little torn. The correct answer is actually, so a middle spoon left out in the sun will heat up very quickly, almost become too hot to touch. This is because, yes, it has a very low specific heat, which means it's not able to, or it's very easy to heat that up, right? It absorbs warmth quite quickly and heats itself up. Whereas high specific heat means something can absorb a lot of warmth and not change its temperature. Alrighty. So I've got a little PhET simulation that I would like you to work on in partner. So I'm going to throw you into randomized breakout rooms again with the idea of, having readers and timers. Share my screen here one more time. We're on task to complete step number 5 right now. You're going to be using PhET simulation titled States of Matter. It'll look like this. You're going to start off in the states program, and then you're going to move on to phase changes. But again, the quiz will give you the instructions on what to do. And so again, the reader is one person should basically be reading instructions and questions out loud so the partner can hear them. Timer, you're just going to keep track of time and make sure that you have both answered the question on your own quiz on your own screen before you move on, right? I want you working together. Shouldn't see one person just racing ahead, the other person sort of falling behind on things. Let me recreate the breakout rooms here. Okay, and let's see. Right on time. So let's time timers. You're going to time for 15 minutes once you're into rooms and once you've decided who's going to be the timer. Well, 15 minutes will put us right at the end. So let's go for 10 minutes. We'll time for 10 minutes once you're in your rooms. So, okay, rooms are open. come back together in 10 minutes. Once you've decided who the timer is, you can start.